Hello and welcome. In this video, we are going to look at basic circuits and their faults. So the first thing we're going to do is look at this first circuit. It has no fault in it whatsoever, so we can calculate it out and measure it and determine what our expected values are. And then from there, we'll identify what the faults are for these other ones. And it's going to show us some key points about how we're going to see the faults in these circuits. So in this first one here, we can measure this out or calculate it. We can calculate it out first. So let's calculate it. We have 5 volts and 220 ohms. So we can find our current. 5 divided by 220. So our current should be 22.7 milliamps. So that's what we expect from this. And so we can use these probe lines here, and these ones are found right up here. They're the green ones here, and there's a voltage one and an amperage one. And when you first pull them out, you see that they've got really small writing on them, and so you can right click and go to properties. And that's going to give you the option to change their appearance. For one, you can go in here and increase the font size to say 14. And then after that, you can also go into the, let's apply that. Go into the parameters here, and we can customize them. And then you can click show twice, and that's going to turn all of these off here. And then you can pick the one you actually want. And we are only working with DC voltage right now, so we'll click yes on DC voltage. And we'll apply that. Okay. And so now we see that it looks like those other ones there, where we've eliminated all that other stuff that's on it. So we know that this circuit here has 5 volts in it. So when we grab our voltage probe and we hit play on the circuit, if we lay that on the line, you see it turns yellow there, and then we can have that voltage probe read out. And we do expect 5 volts at the beginning here, and we expect 0 volts at the other side, right? Because this resistor here is going to consume all of the voltage that we give it. So 5 volts drops across that resistor, we're left with 0 at ground. And so our current, we know that it should be this 22.7 milliamps. And so we'll place our current probe, and that's this amperage probe up here. And we see that it's negative. That's fine. Current is never negative, right? Because time is not negative. But we can right click that and rotate, say, reverse probe direction. And that's going to point it in the other direction. It's just the arrow at the end of that amperage probe. And that allows us to measure around here and say that it's 22.7 all the way to ground. And that is what we expect, right? Both sides of that should have 22.7 milliamps across it. And so this circuit is measuring correctly. It matches what we expect it to have. So let's do that for this other faulted circuit over here. We can say that the voltage at the beginning should be 5 volts. And we get that. That's 5 volts. The voltage at the end should be 0 volts. We get that. 0 volts. So far our voltage told us nothing about what's wrong with this circuit. There's definitely a fault in this circuit. So we have to measure our current. So grab our current probe and we'll pull it over here. We know it should be 22.7 milliamps. And we get 5 picoamps. Picoamps is really, really, really small, right? So there's no current. 0 amps as we rotate around that corner there, and 0 amps at the end. There's no current in this circuit, right? That means we must have an enormous amount of resistance to stop all of the current when we know that we have a voltage potential. We know that we've given it 5 volts, but the resistance is so large that no current can pass through there. And we will call this an open fault. An open fault. So let's click on this little thing here. It says an open fault has infinite resistance. And an open fault in series has the source voltage across it. We saw that 5 volts still dropped across that. This is the most common fault for a series circuit. So an open is how our resistors will fault naturally. So let's check the next one down here. We'll grab our 2 voltage probes. We know that that one is definitely an open circuit there. So when we move down here, we'll check our voltage on this one. This one says it's 5 volts on this side. That's what we expect it to be, 5 volts there. We expect this side to be 0 volts there. So we do have a voltage drop across this 220 ohm resistor of our full voltage drop. So it told us nothing about the circuit so far. When we measure our current, it's got 5 gigaamps, right? Gigaamps. That's really, really, really big. That means that this resistor is really, really, really small, right? Because resistance and current are inversely proportional. So if we have a lot of current, we must have very, very little resistance. And in this case, probably no resistance. So that means that this resistor has a shorted path around it. Something is shorting the current in a different pathway around that resistor. That resistor itself still has resistance, but there's something else that's allowing that current to flow around that resistance. And so we expect this to be a short. A short has 0 ohms of resistance. There's one more circuit down here, so we'll move down one more as well. And this is our final fault that we will see on our basic circuits, on any circuit. We'll see that we have voltage on this side here, just like we usually expect, 5 volts there, 0 volts on the other side. So yet again, that voltage measurement didn't really tell us anything. And so we'll go after our current. And our current says that we have 134 milliamps, and we should have had 22.7 milliamps. That's what we calculated. So we can figure out what that actually means for us. Let's follow it all the way down. We said that current leads all the way down. So we have current, we have voltage, we have resistance, but we don't have what we expect. So let's calculate what we actually have here. We know that we have 5 volts, and we can divide that by the current we actually got, which is 0.134. So we actually have 37 ohms of resistance here. Instead of 220, we have 37, which means that this resistor is leaking. It has a leakage, or it's a partial short. Right? And that's what we expect from that. So if you do come up with something that does not match what you actually expect it to be, your actual calculated value, you can take the measurement and you can use that to calculate out. Okay, let us know if you have any questions.